everybody, welcome back to Mathematical Statistics. We are talking about maximum likelihood estimators. Today we're going to finish up proving some of the properties in our list of good properties for maximum likelihood estimators. And next time we're going to really begin our journey towards the UMVU, the uniformly minimum variance unbiased estimator, the best estimator in all the land. So that doesn't mean we're hitting the UMVU next time. We have some machinery to build up, and we're going to talk about something known as sufficient statistics next time. But today, let's do a little more MLE stuff. We had a list of 5 things that were mostly asymptotic properties. And let me remind you of a definition before I list the last 2. So let me get my screen. Okay, so we've been talking about estimators of like a tau of theta, but really everything we're talking about today is going to be for theta, so I think it'll be a little simpler notation-wise to think of it that way. If we have an estimator, be it an MLE or not, if this is an unbiased estimator of some parameter theta, we define the efficiency of this estimator to be the Cremier-Rao lower bound for the variance of all unbiased estimators of theta over the actual variance of this estimator. So efficiency is usually defined for unbiased estimators. I'll come back and say something about that in a moment. But if you have an unbiased estimator, we know that the variance is always greater than or equal to the Cremier-Rao lower bound, which means that this quantity is less than or equal to 1. It is possible to talk about efficiency for biased estimators, in which case the variance might actually drop below the Cremier-Rao lower bound, and this number will be greater than 1, and we would call that a super efficient estimator. But I personally don't like to talk about efficiency when we have biased estimators. I don't think it makes that much sense. So this is our definition of efficiency. I mean, I should have some notation here, but I don't really have notation for this, nor will we need it. Maybe something like that. But we also talked about asymptotic efficiency, which is property 4 that we're starting with today. Actually, before that, let me say that the estimator theta n hat is an efficient estimator of theta if this efficiency, guess I'm sticking with this notation now, is actually equal to 1. So property 4 in our list of MLEs is not about efficiency. In fact, our MLEs are not even usually unbiased. So whether or not you want to talk about efficiency in that case is up to you. But the property 4 does not say that MLEs are efficient. It says that they're asymptotically efficient. And we've already seen that they're asymptotically unbiased. So in the limit, things are getting nice all the way around. So let me write that property down. This is property 4 in our list of properties of MLEs. So as a setup here, I'm going to let theta n hat be the maximum likelihood estimator for theta. And I'm going to say the because we're in a list of a bunch of properties and we've been picking out some conditions that we need as we go. And the first thing in our list of properties was that the MLE exists and is unique. So I'm writing this under the assumption that it is unique and does exist. So I'm not going to say an MLE. And property 4 says that the MLE is asymptotically efficient, or an asymptotically efficient estimator of theta. So this means that if you look at the limit as n goes to infinity of the Cremier-Rao lower bound for theta over the variance of that MLE, that this goes to 1. It may not be efficient along the way. It may not be efficient for a finite sample size n, but as n goes to infinity, it becomes efficient. In the interest of moving it along and also thinking about what I'm about to do next, I am going to skip the proof here, but you can kind of see this result in the next property, our final property for MLEs. So it was about asymptotic normality. And so under certain regularity conditions involving certain variances being finite, certain logs existing, things like that, we've got that the MLE for theta is asymptotically normal with the correct mean, the thing we're trying to estimate, which is theta, and variance actually equal in that limit to the Cremier lower bound for theta. I forgot our new notation. So just in this sequence of 5 properties for MLEs and our proofs, because the theta was or is a variable for a likelihood, I do want to nail down a theta that generated the data. So let me be a little more specific here. Suppose we have x1 through xn, IID from some PDF, some distribution with PDF f of x and theta naught. So theta naught is our specific theta that generated the data. I mentioned last time that I'd be using this for these proofs, again, because I want theta to be a variable for my likelihood. And I'm going to stop using this notation after this section today. And we'll go back to just saying IID with parameter theta. So with that, I need to update my results here a little bit. This is going to be normal with asymptotic mean theta naught and asymptotic variance equal to the Cremier-Rao lower bound for the variance of all unbiased estimators of theta naught. Before proving this, let me maybe simplify the statement a little bit, or I don't know if this is a simplification, but let me make it a little more specific. The Cremier-Rao lower bound for the variance of all unbiased estimators, right? This is supposed to be the derivative of tau of theta squared over the n-dimensional Fisher information, and I've got all theta naughts now. And our tau of theta, just it's a function, right? So I don't need to put a theta naught in there if I want to just describe the function, is just theta, which means that this derivative is going to be 1. By the way, tau prime of theta naught is really the derivative with respect to theta of tau of theta evaluated at theta equals theta naught. So it's not a derivative with respect to theta naught. Theta naught is constant. It's not moving. There's no rate of change to even consider for theta naught. But going back over to this unfinished statement, the Cremier lower bound is going to be 1 over the n-dimensional Fisher information evaluated at theta naught. And let's, because I'm assuming IID, simplify this a little further. We know in the IID case that the n-dimensional Fisher information is n times the one-dimensional Fisher information. That is the information based on a single variable from the list x1 through xn. So if this MLE is asymptotically normal, like this, specifically that means, so i.e., the MLE minus theta naught over the square root of 1 over n times the one-dimensional Fisher information at theta naught, this needs to be converging in distribution to a normal 0, 1. That's what this asymptotic statement says, and that's what we want to prove. Let me clean this up just a little bit and flip that denominator up. This is saying that the square root of n times the one-dimensional Fisher information times the stuff is converging in distribution. So I'm just rewriting the left side. And I think it's going to be, we could show this, but it's going to be a little more convenient to move this to the right side of this statement. If you imagine multiplying by 1 over the square root of this Fisher information on both sides, normal 0, 1. This is some constant, right? We've taken derivatives, we've taken expectations, and we've plugged in theta naught for theta in the end. So it doesn't, there's no, it's a constant, right? And if you multiply a normal by a constant, you get to multiply the mean by that constant, but the mean was 0, so the constant times the mean is still 0. And it will go into the variance, but squared. So 1 over this one-dimensional Fisher information evaluated at theta naught. So just to clarify or sum that all up, we're going to show that the square root of n times the MLE minus the parameter that generated the data is converging in distribution to a random variable that has this normal distribution. And you might give that random variable a name, like z, although that would maybe look like a standard normal, and this is not quite a standard normal. So this is what we're out to show now. Let's consider a Taylor polynomial. Recall that if you have a function f, which this is just me restating Taylor polynomial stuff. This is not the PDF, so this is just sort of an aside. But if you have a function f and you expand it around a point c, you can write this as f of c plus f prime of c times x minus c plus 1 over 2 factorial f double prime of c times x minus c squared plus 1 over 3 factorial, etc. But if you cut it off, and I'm going to cut it off here with this term, then you don't put the c in. You have a second derivative, and you have some xc, not a c, but a xc, x minus c squared for some xc between x and c. And I write it out like that the long way rather than writing some kind of inequality because the c is going to be a fixed number that we're expanding about, and the x is a variable. So the x might be above c, it might be below c. So that's why I'm not just saying, I'm not writing an inequality with the c in the middle. All right, we're going to use this, and again, that's not the PDF, that's just reviewing a Taylor polynomial. Here, the f is going to be L sub n prime. Now, if I get too sloppy here, that's going to be confusing. I'm continuing with our notation from last time. We have a log likelihood, which is like ln of the likelihood. And I realize this looks a lot like this, but what this is f of theta equals ln prime theta. It's really this, with us using expanded notation to show the dependence on n. So that could be confusing, but this is the log likelihood and the derivative of that. This is really this, but it's derivative. But then showing that this actually depends on n. So adding a subscript, which looks a lot like this, but they're different. Okay, so here, let me get rid of that. That's gonna mess up our proof a little too much. This is gonna be our f, and our x is going to be the MLE, and our c is going to be theta naught, that parameter, that specific number that generated the data. And then, yeah, let's write this out. So I'm just going to rewrite what's at the top of the screen with all of these things plugged in. I'll get the log likelihood derivative evaluated at the MLE. Oh, we know what that equals. That is 0. Because how do you find the MLE? You sometimes look at the likelihood, sometimes the log likelihood, but you take its derivative and set it equal to 0 and find a solution to that. So if you were to plug that MLE back into the derivative of the log likelihood, you should get 0. And continuing my rewrite of the Taylor polynomial, this is the log likelihood derivative at theta naught plus the log likelihood second derivative at theta naught times the MLE minus theta naught plus 1 over 2, which is 2 factorial, the log likelihood third derivative, I'm going to leave this blank for a moment, theta n hat minus theta naught squared. So this has to be something that is between these two things. But one of those things in what we're doing is random. The MLE is a random variable. And so if you're trying to be between a constant and a random variable, then that thing between them needs to be random. So it could keep up with the one random endpoint, possibly moving and switching sides. So I am going to plug in here a theta and tilde, and I'm going to say where theta and tilde is a random variable between the MLE and theta naught. Okay, remember this side is 0, and I should probably write a new line with that zeroed out to clean it up, but I'm not going to. We kind of have a long journey ahead. So what can I say about these terms here? By MLE property 2, this was the one where we said that, or we showed that MLEs are consistent estimators of theta naught under some mild conditions about like having a finite variance or a finite second moment. We know that the MLE converges in probability to that value that generated the data. So this means that the MLE minus theta naught is converging in probability to 0. And this means that the MLE minus theta naught squared is also converging in probability to 0 by the continuous mapping theorem. So if we go back up to the top line here, this is going to 0, but I can't say the whole term is going to 0 because I don't know what's happening here yet. This one is also going to 0, and we're going to talk about what's happening here. And this last one over here is going to 0 faster than this one. So I am about to do a little hand waving about things getting negligible faster than other things getting negligible. If you are familiar with and comfortable with little o arguments in analysis, and more specifically, the analog in probability, which are called little op arguments, you actually would write little o of p, then you can do this a little more formally rather than saying this thing is negligible. It has a specific meaning about how it's going to go to 0 when you divide by a certain thing. And I think I'm going to leave that out of it, but later we will do a proof with a little o of p argument. And if you look at how we do that, that would be the patch to this one step of this proof. Okay, so I was saying that this goes to 0 and this goes to 0, but this goes to 0 faster. And I'm trying to say that this entire term is kind of negligible faster. But it does depend on what's happening here. And this is going to add another regularity condition to our list of things. We're going to assume that the third derivative of the log likelihood, and right now I've just written it as a function of theta, we're going to assume that this is bounded by a constant that is independent, you might say uniformly bounded, independent of n and theta. So something that's going to hold for all n and theta. This is this assumption should be added to the list of regularity conditions. And if it's bounded, we're almost ready to say if this goes to 0 and this is bounded, then that whole term is going to 0. However, in our third derivative of the log likelihood, I have plugged in something strange, something random. And so this may be bounded, but like if this is not, let's just look at what this is doing. Is it converging at all? Um, I claim that this theta n tilde, this random point between our MLE and the value we're estimating, converges in probability to theta naught. So a mini little proof here of this claim. Remember that theta n tilde was between theta n hat and theta naught. So let me write that down. Between theta n tilde and theta naught implies that theta n tilde is closer to theta naught than the MLE. Specifically, if we take any epsilon greater than 0 and consider the distance between theta n tilde and theta naught, and look at the probability that the absolute value of this difference is greater than epsilon, this is going to be less than or equal to the probability of the same sort of thing, but using the MLE, not theta n tilde. Because again, this is closer to this than this is closer to this. So this is a larger distance than this. It's going to be easier for this thing to be greater than epsilon than it is for this thing. So it will happen with a higher probability. Get rid of this mess. But as a final line for the proof of this little claim, if you take the limit as n goes to infinity on both sides here, this right side goes to 0 since by property 2, because the MLE is a consistent estimator of theta naught. That means it converges in probability to theta naught. And then this limit is going to be stuck below the limit on the right-hand side, and it's a probability. It can't get negative. So this inequality and taking the limits across imply that the limit as n goes to infinity of this probability being greater than epsilon is going to 0, which is enough to say that it's one of the definitions of convergence in probability for the random variable theta n tilde. Okay, so back up to our expression here. I've decided to make the assumption that this is bounded no matter what you plug into it, and that and for all n, and that this is not doing anything weird in terms of its convergence. It's going to a constant. So that's going to make this whole thing bounded. And with this going to 0 and this being bounded, this final term, I claim, is going in probability to 0. And again, this is something known as a little o of p argument. And this may be going as well. This certainly is, but we'd have to talk about this. But that final term is going faster. And so what's actually happening in the limit is more dominated by this term. Like this term becomes negligible faster. So here's what I'm trying to say. On the left-hand side, we had the log likelihood derivative evaluated at the MLE, and that was 0. On the right-hand side, we had the log likelihood derivative at theta naught, plus the log likelihood second derivative at theta naught times the MLE. Let's make this a new bullet. Minus theta naught plus something negligible. And using little o notation would make that much more precise. Disappearing and disappearing fast. What you could do is leave that term there and do everything we're about to do and deal with that term. But in the interest of brevity, clarity, and time, I am going to say that we get approximately 0 out of these first two terms, we're going to take a limit. So I made some curvy lines, but I didn't make them that curvy. I'm trying to slip that by you and make it look equal. Let's assume they're equal. Otherwise, we could say they're equal plus some negligible term, and we could use good notation or not. This implies that the MLE minus the value that generated the data is equal to the negative of the first derivative of the log likelihood evaluated at theta naught over the second derivative of the log likelihood evaluated at theta naught. And remember what we wanted to show. We wanted to look at the square root of n times this and show that this goes to a normal distribution with mean 0 and variance 1 over the one-dimensional Fisher information. So I'm going to put the square root here, and actually well, I could put the negative anywhere. Let's put it here. There's our first derivative and our second derivative. And so we want to show that this goes in distribution to a normal 0, 1 over the one-dimensional Fisher information. That's the plan. I bet you can, I don't know, does anyone else feel that Slutsky's theorem is coming? Like we've got a numerator that's maybe going to something and a denominator that's going to something, and we'll combine them using Slutsky's theorem? I feel that. Let's look at part of the numerator. I'm going to ignore the negative for now and the square root of n for now. This is the derivative of the log likelihood evaluated at theta naught. So specifically, because our random variables were IID, our joint PDF was a product of individual PDFs. We're going to take that product of individual PDFs to be the likelihood. When we take the log of that product, we'll get a sum of logs. And so this is the sum as I goes from 1 to n of the, oh, and then we're taking the derivative. So of the derivative with respect to theta of the log of f of xi and theta naught. Again, what this means is this is the derivative with, so I don't have a theta naught over here. The reason is what is meant by what I just wrote. This is the derivative with respect to theta of the log of f of xi, and theta evaluated at theta equals theta naught. Right? It's kind of like just having a function, this is not the PDF, but just having a function f and taking a derivative and plugging in a 3. You're not taking the derivative of f of 3. The 3 is going in after the derivative with respect to something like an x. Okay, I'll move that because this is already pretty long and messy. I want to get normality. I think we need a central limit theorem. Let's look at 1 over n times this thing. This is a sample mean. This is a like W bar where, I don't know why I used a W. I'll probably use a Y, but where Wi is the derivative with respect to theta of the log of the PDF evaluated at capital X sub I and theta naught. I'm going to use a central limit theorem on this sample mean. So we need to know its mean and variance, or at least the mean and variance for one of these. The expected value of Wi is the expected value of the derivative of the log of the PDF evaluated at capital Xi, so there's some randomness, and theta naught. And this is the score function that we saw in our first computational simplification for Crumier-Rao lower bound computations. The expected value of the score function in that property we showed was 0. How about the variance? The variance of Wi is going to be the expected value of this thing all squared minus the expected value of the thing, and then a square on the outside. But we just said that this is 0. So it's really just this piece. And that is a one-dimensional Fisher information right there, right? This is a single X, not a vector. And this is the way we define Fisher information when we're using the first derivative as opposed to the second derivative. So this variance is equal to I1 of theta naught, because this guy right here is the Fisher information for one of the random variables. Okay, let me try to recap that. We had 1 over n times the log likelihood derivative at theta naught. We wrote it as a W bar, and we're trying to apply the central limit theorem. And so this is asymptotically normal. The mean in the asymptotic distribution is the mean of one of the W's, and we figured out that that was 0. And the variance is the variance of one of them over n. Remember, like sigma squared over n. And we just show that this is the variance for one of them. So I1 of theta naught over n. In particular, this asymptotic statement says that 1 over n times the first derivative of this log likelihood minus 0 over the square root of I1 theta naught over n is converging in distribution to a normal 0, 1. Okay, what were we doing? We are looking at this expression. In fact, let me copy and paste this down. I need a little bit of this. Move this down. Get rid of that. We just said something about this. When you have a 1 over n in front and you divide it by something and all of that. So let's, I am going to rewrite this whole thing. I am going to put the negative, sorry, I keep erasing everything. I'm going to put the negative in the denominator. I think you might see why, because we are getting terms that involve the Fisher information. And one of them was an expected value of something squared, and the other was the negative of an expected value of a second derivative. I am also going to get that square root of n down in the denominator. And I am going to put 1 over n in front of the numerator and the denominator because I want to sort of see this. Keep erasing. Sorry. So this is equal to 1 over n times the derivative of the log likelihood at theta naught divided by the square root of the one-dimensional Fisher information at theta naught divided by n over negative 1 over n times the log likelihood second derivative divided by, so I'm trying to make this equal to the line above. So I need to divide by the square root of I1 theta naught over n. I made that seem way harder than it had to be. They put that together in a very strange way. I had a professor once that used to draw cubes, like a cube like this. Like it was just the most bizarre sequence of steps. And I feel like that's what I'm doing right now. So sorry about that. But this is equal to the line above. I'm actually missing this square root of n. I get rid of all of these, put that in the front here. Something like that. Now this is definitely equal to the line above. And what do we have? We've got this is converging in distribution to a normal 0, 1. Here I have a square root of n. in the denominator of the denominator. So that is going to end up canceling with this one. Okay, so we have the square root of n, the MLE minus the value that generated the data is equal to 1 over n, the log likelihood derivative evaluated at theta naught, times the one-dimensional Fisher information at theta naught over n over negative 1 over n log likelihood second derivative at theta naught. This should be divided by square root of the one-dimensional Fisher information. And again, we know that this goes in distribution to a normal 0, 1. Now remember, we're trying to show that this left side is converging in distribution to a normal 0, 1 over I1 of theta naught. So hopefully this denominator is converging to this. Or I'm sorry, hopefully the denominator here is converging to the square root of this. So then when you take 1 over the square root of this times this normal 0, 1, that's how you get the thing we're trying to get, the normal 0, 1 over the one-dimensional Fisher information. Marks everywhere. All right, let's look at the denominator. I'm just going to start with the negative 1 over n log likelihood second derivative at theta naught. This is 1 over n times the sum as I goes from 1 to n of the negative of the second derivative with respect to theta of the log of the PDF with xi in it. And then that derivative, there should be a theta in there, but ultimately evaluated at theta naught. This is another sample mean. You see a 1 over n and a sum of n things. But rather than use the central limit theorem here, I'm going to use the weak law of large numbers. So this is like a y bar where yi is the negative of this second derivative, etc. And so by the weak law of large numbers, assuming that the variance of one of the terms is finite, which is a Fisher information term, which we're assuming, which should be finite, or none of this makes sense. This converges in probability to the mean of one of them. This is me trying to say that y bar converges in probability to the mean of one of them. But what is the mean of one of them? That is the expected value of one of these terms. So the negative second derivative of the log of f of, say, x1 and theta naught. And this is the one-dimensional, remember there's a negative there, it's hard to see. This is the one-dimensional Fisher information evaluated at theta naught. That was our property 3 for computational simplifications. We could define the Fisher information with a certain expectation of something squared, or we could not have a square but have a second derivative. Let's look at the entire denominator. Negative 1 over n log likelihood second derivative with theta naught plugged in divided by the one-dimensional Fisher information is going to converge in probability to the one-dimensional Fisher information over the square root of the one-dimensional Fisher information. And if you multiply by a couple of those square roots, can make this a little cleaner. On the bottom, we get the one-dimensional Fisher information, which is going to cancel it with the top. So we get this whole thing equals the square root of the one-dimensional Fisher information. Let's bring it on home. We have it all, but let me try to summarize. We were looking at the square root of n times the MLE minus theta naught. We had written it as 1 over n times the log likelihood first derivative at theta naught divided by the square root of the one-dimensional Fisher information at theta naught over n over -1 over n, the second derivative of the log likelihood, divided by the square root of the one-dimensional Fisher information, which is right here. And we know that this goes in distribution to a normal 0, 1 random variable. And this goes in probability to the square root of that one-dimensional Fisher information. So when you divide a normal by a constant, if it's a standard normal, it's not going to affect the mean. But if this is a normal 0, 1, then we're going to get 1 over c squared in here. And this is the c. So we've got the square root of n, the MLE, minus the thing we're trying to estimate, converging in distribution to a normal 0, 1 over the one-dimensional Fisher information by Slutsky's theorem. And we're done. That's what we wanted to show. With a little hand waving about that third derivative term. That was pretty darn cool, if you ask me. Okay, to finish off today, I want to do a kind of long MLE example. Certainly not going to be our last brush with MLEs. We're going to be seeing them all the time, but it's our last official example in this section before we move on to UMVU territory. And I want to pull a whole bunch of things together from our list of properties here. This problem came off of a statistics graduate qualifying exam at a particular university, which means that, does it mean that it's hard? It doesn't mean that it's hard. It means that it looks different. It might be a little scary. But again, as I've said before, if you just keep your wits about you and keep breathing and moving forward, you're going to get this. You're going to get this. So here is my example. It involves a gamma distribution, actually several gamma distributions. So I'm going to suppose that I have not x1 through xn yet, but constants, little c1, little c2 through little cn. They're going to be positive, and I'm going to let these be known constants. I'm going to suppose that x1 through xn are independent random variables, but I'm not writing IID because they're actually going to have different distributions, not wildly different like Pareto and beta, but they're all going to have gamma distributions with different parameters. So with xi having a gamma distribution, now the parameters in this problem were given in terms of the mean and variance. So we're given that the expected value of the ith one was 2 times theta times ci, and we're given that the variance was 2 times theta ci squared. I'm not entirely sure. I probably should have done the problem both ways and seen which came out nicer, but I'm not entirely sure what this exam at a given university meant by this gamma distribution, if they have a beta or 1 over beta. I am going to finish this problem as if this is the mean and variance, and we're using our notation. So in our notation, we have like an alpha and a beta, and the expected value of xi is alpha over beta. And we're saying here that that's 2 theta ci. So what I'm trying to do is find these in terms of the given parameter theta. And in terms of our notation for the gamma distribution, the variance is alpha over beta squared. And this is 2 theta ci squared. So looking at this system of equations, if you think about it a bit, maybe actually solve and move things around, this gives you that alpha is 2 and beta is 1 over theta ci. using our parameterization of the gamma distribution. By the way, if you are in this class and you're taking the qualifying exam and something like this comes up, I didn't necessarily write that exam. So I would ask the proctor to clarify what is meant by the gamma distribution. Are they using the beta or the 1 over beta? That's perfectly fine to ask for clarification. If you don't get clarification, which I don't see why you wouldn't, I would continue on my exam by saying, I am assuming that, because they really care more about you knowing what you're doing and your skills and your common sense and all that sort of stuff. So if the problem wasn't easy to interpret for you, that's really not an issue. Maybe that's a poor choice of words, but okay. So let's recap. We have constants C1 through Cn that are positive and known, and we have x1 through xn. They're independent with xi having a gamma distribution with parameter 2 and 1 over theta ci in our gamma distribution notation. So what's the problem? I didn't write down any problems yet. This is going to have 3 parts. In part A, I want to find the maximum likelihood estimator for theta. We got to write that down a likelihood. We got to start by writing down a joint PDF. So let's do that. The joint probability density function, this is f of a vector of x's and theta, and they are independent, so we do get this from a product, but they're not the same distribution over and over again. So usually I have like an f of xi and theta here, but that's one f over and over again. So I'm going to write this as f sub xi because the function is actually changing. And let's fill in what it is. I've got the product as I goes from 1 to n, and then this PDF. So 1 over gamma of 2. Then we have beta to the alpha, which is 1 over theta ci to the 2. Then we have xi to the alpha minus 1, so 2 minus 1. And then e to the minus beta xi, which is going to be xi divided by theta ci. Let's multiply this out. Now gamma of 2 is equal to 1, so that disappears. And we get, look at these terms here. I've got a 1 over theta squared appearing in each of the n terms in this product. So I've got a 1 over theta to the 2n. Okay, so now I'm going to deal with the ci squared and the xi to the first power. I'm just going to write this as the product as I goes from 1 to n of xi over ci squared. And now I'm going to take the product of this, which is going to be e to the minus the sum of all of these. Now I'm going to pull out theta, so minus 1 over theta, the sum as I goes from 1 to n, xi over ci. There is the joint PDF. And yeah, I left off the indicators, but for maximum likelihood estimation, well, you know the drill. It's not going to matter if the parameter is not in the indicator, which it's not. Okay, I'm going to write down a likelihood. You could take the entire joint PDF, or you can knock off some constants of proportionality. So if there was a 3 in front of this, you could cancel it, multiplicative constants of proportionality. Note that this term right here is constant when you're thinking of this with respect to theta, when you're thinking of this as a function of theta. So I'm going to drop it and take my likelihood to be 1 over theta to the 2n e to the minus 1 over theta sum as I goes from 1 to n of xi over ci. My x's are lowercase. You could make them uppercase. We're just doing algebra at this point. We're not trying to give an estimator. But this definitely looks like one of those likelihoods where taking the log would be a good idea. So the log likelihood, we have theta to the negative 2n. So the log likelihood is negative 2n log theta minus 1 over theta, the sum as I goes from 1 to n of xi over ci. Let's take the derivative. We get negative 2n over theta. And then this is a theta to the negative 1. Its derivative is negative theta to the negative 2. And combining that negative with this negative, we're going to get plus 1 over theta squared, the sum as I goes from 1 to n of xi over ci. Let's set this equal to 0. I am going to take care of these denominators by multiplying the left side and the right side by theta squared. For the first term, I'll cancel one of those thetas, and we have minus 2n theta. For the second term, the entire theta squared will cancel, so I get plus the sum as I goes from 1 to n of the xi over ci equals 0. And as a final step, let's solve for theta, make everything capital and random, and put a hat on it. This will be our MLE. This is 1 over 2n, the sum as I goes from 1 to n of capital Xi over Ci. This is the MLE, and yes, you should take a second derivative of the log likelihood to make sure that you didn't minimize the MLE. If you're in a qualifying exam or something like that, I would move on from here. I would make a note. I should check this. And then if you have time at the end, actually check it. But you want to show the graders of the qualifying exam that you know the math stat part, really. And I'm just speaking for, well, I guess myself, but for us here in APPM, that's usually what I think everyone would agree with that statement. If you're at another university, that's still my advice. Okay, so in part B, I think I won't have time to finish this, but I want to know if does the variance of this theta hat achieve the Cremier-Rao lower bound for the variance of all unbiased estimators of theta. By achieve, I mean equal. The variance should be, for an unbiased estimator, should be larger than the Cremier-Rao lower bound. And if it's efficient, we should get them equal. What this question is asking, is find the variance of this estimator, find the Cremier-Rao lower bound, and compare them. Are they the same or not? I think in the time we have left, we can get the variance done at least. And then when we come back, there'll be a part C of the problem where I want to actually do a hypothesis test for theta for this weird setup. And if we can, I want to make the test based on this statistic. And if we can deal with the exact distribution of this and we can get critical values, great. But if not, then we're going to use asymptotic normality of the MLE and say a large sample approximate hypothesis test is. But that'll be next time. So let's just find this variance and call it a day. The variance of theta hat, you might call it theta n hat, is the variance of 1 over 2n, the sum of the xi over ci. I'm going to pull the constant out, but it comes out squared. So 1 over 4n squared. I can pull the sum into the variance only because they're independent. So you better say that. Then I get the sum as I goes from 1 to n of the variance of xi over ci. And then I'm going to pull this constant out of the variance squared. So I get 1 over 4n squared. The sum as I goes from 1 to n of 1 over ci times the variance of xi. I'm thinking now that the writers of this problem meant to use, that they were thinking of the gamma distribution in the alternate parameterization because this would have been cleaner, but we can do it. We can do it. The variance of xi we know is, what was it? It was 2 theta ci squared. So if we cancel this and part of this and this and part of this and move things around, we're going to get 1 over 2n squared, a theta squared that can come out. Okay, so there's the variance. Next time, we're going to find the Cremier lower bound, and we're going to compare this to that, and then we're going to do a hypothesis test concerning theta, and then we're going to move on into UMVU territory, the uniformly minimum variance unbiased estimator, the greatest estimator in all the land. Although, fair warning, we're not going to get to that. We have to build up quite a bit of machinery, which is going to be interesting in its own right. So I hope to see you next time on Mathematical Statistics.